Alabama STEM Explorers is made possible by the generous support of Hudson Alpha Institute for Biotechnology, Southern Research, solving the world's hardest problems, the Holly Family Foundation, Alabama Works, Alabama STEM Council, Alabama Mathematics, Science, Technology, and Engineering Coalition, Alabama Math, Science, and Technology Initiative.
I love a good cup of tea in the afternoon, so I'm gonna add some sugar to my water. Isn't this a cute little coffee tea beaker? It's kind of chemistry looking.
It is.
Yes, so I'm gonna add some sugar. Anderson, will you grab that spoon? Will you stir this up for me?
I think I might have broke your spoon.
Where did my spoon go? Let's go outside and investigate this a little bit more.
Hi, and thanks for joining us on today's episode of Alabama STEM Explorers. I'm Anderson.
And I'm Kathryn.
And today we're coming to you from Southern Research in Birmingham, Alabama.
And we are going to explore the difference between chemical changes and physical changes. And we're going to take a look at this magic spoon. This spoon wasn't really magic, it was just an example of a physical change. And so in science, we often classify changes as being either physical or chemical. And so a chemical change is something that is going to produce a new substance. And so, and physical changes don't. So example of chemical changes would be things like burning wood or rusting iron or dyeing your hair, right?
I'm a natural blonde.
Okay, Anderson. But in a chemical reaction, there's always a chemical change that's taking place. And so the starting materials and the ending products are different, but a physical change, not so much. And so let's take a look at some examples of a physical change. So Anderson, will you rip this paper in half? All right, so has a new substance been formed?
No.
No, so this would be an example of a physical change. Pretty easy. What about this? Will you crinkle this aluminum foil? New substance?
No.
I didn't think so. That's right, no new substance. Now this is a little bit trickier. So here we have a beaker of ice and we have a cup of water. And so as this ice melts, is there a new substance?
No.
No, that's right. It is just water. And so oftentimes physical changes are just a change in the state of matter. So going from a solid to a liquid would be melting. Or in this case, do you know what this is on this plate? Give it a blow. You can blow on it a little bit. Yeah, do you know what this is?
Dry ice.
It is dry ice, which is what?
Ooh, it's frozen carbon dioxide.
That's right. So dry ice is just frozen carbon dioxide. It is frozen gas. And the cool thing about dry ice is that it never goes to a liquid at atmospheric pressure. It goes directly from a solid to a gas. And so again, it's just an example of a change in a state of matter. So from solid to gas. So as this dry ice sublimates, is there a new substance being formed?
No.
No new substance, right? And so this is another example of a physical change. Now, for the experiment I know you have been waiting for, our magic spoon. So we will do this again for our viewers to take another look. So here is the spoon. Will you stir this cup of water for me, Anderson? This cup.
Oh, this cup?
Yes. And there it goes. You want to pull that out and you see? Okay, so I will explain to you guys what is going on because it really isn't magic. It is just an example of a physical change. And so this spoon is made of gallium, and gallium is just, it's a type of metal, and it melts at 30 degrees Celsius, which is about 86 degrees Fahrenheit. And so when you almost put it in this beaker, I caught you because this water is not warm enough to melt the gallium, but this one is a little bit warm water, and so when you put it in there, it just kind of melts away. And so this is an example of a physical change because this is also reversible. How do you think we could reverse this?
You could get what's left in the bottom and then put it in the mold again?
That's right. So what we have over here, this is just a mold, and you can kind of buy these little kits online. They're pretty easy to find. Great prank to play on some family and friends. But yeah, you can just collect the gallium that's at the bottom of the container, and then we use this syringe whenever the gallium is in the liquid state, and we just put it into the mold, and it is a solid gallium spoon. And you can play with these all day long. They're a lot of fun. And make for a pretty great prank.
So gallium won't melt in cold water?
No, we could try it out actually. Do you want to? Yeah, so it's pretty normal. Yep, so it's not going to melt. It's not going to melt in colder water. So let's head outside and take a look at some larger scale demonstrations that show physical changes.
But this is something you can't do at home. Make sure you have a scientist and a safety professional.
All right, so I am so excited. We are about to do our first experiment, and this is what I call the ultimate ping pong party. So what we are going to do is we're going to look at a physical change by using liquid nitrogen. And so liquid nitrogen is just really, really cold air. So most of the air that we breathe is nitrogen. It's about 78% or so. But liquid nitrogen is just the liquid state of that gas nitrogen. So if you get nitrogen really cold, like negative 196 degrees below zero, it is going to be a liquid, all right? And so what that means is that at room temperature, that liquid nitrogen is going to constantly boil. All right, and the liquid to gas expansion ratio is around 1 to 700. So meaning the amount of space that liquid nitrogen takes up as a liquid, it's going to take up 700 times that amount of space as a gas. It's absolutely nuts, all right? And so for this experiment, what we need to do is we need, or a couple things we need is liquid nitrogen, a 2-liter bottle, a funnel, a giant trash can, 1,000 ping pong balls, and my good friend Liz. Hi. So Liz is a scientist here at Southern Research, and she is going to help us out. And again, this is an experiment that definitely you do not want to try at home. We're both trained scientists, and we have safety professionals on hand, but it is definitely fun to watch, so you can definitely watch it at home. So first thing we're going to do is we are going to put on our masks.
Oh, goodness.
Oh, yeah, you're looking good, Anderson. All right, and then I'm going to put on these cryogenic gloves. And Liz is going to help me with this. So she is going to hold this funnel, and we are going to pour the nitrogen inside of this 2-liter bottle. And you can kind of pull that funnel out a little bit, Liz. Whenever I pour it in there, it kind of helps it go in. There you go.
It looks like steam coming up from a train.
Yeah, this is actually just fog. I mean, it's condensation. It's kind of like a little cloud. All right, we only want about maybe 1 or 2 inches at the bottom. How does that look? Yeah, I think that's pretty good. All right, so this is what we're gonna do. We're gonna walk on over to this giant trash can over here. This way. All right, and so what I'm gonna do is I'm gonna cap this bottle off, and remember that liquid is gonna expand to 700 times the amount of space. As soon as I cap it off, I'm dumping it into this trash can. Liz is gonna dump those 1,000 ping pong balls, and then we're gonna run. Are you ready? All right, so here we go. We're capping it. All right, now we're gonna run this way. Oh no! That's good, Anderson, you can come up here. All right. So now what's happening inside of that bucket is there is a crazy amount of pressure, right? So that liquid is boiling. Oh, yes! Yes! Oh, that was so cool!
Oh my gosh, is there more?
That is like the ultimate birthday celebration. All right, so for this this next experiment, we're gonna do the same type of physical change. So we're gonna watch we're gonna use liquid nitrogen and just see it go from a liquid to a gas. So it's gonna be the same experiment, but with a little bit of a twist. So instead of a ping pong party, we're going to do a liquid nitrogen trash can rocket, all right? This is actually probably my favorite experiment of all time. It is so, so cool. All right, are you ready to go?
I am definitely ready.
All right, so we're gonna do the same thing as before. So there we go. Thank you, Liz. Liz is gonna hold that funnel, and remember this nitrogen, I mean, right now it is on fire. It is so unhappy because it wants to be in a liquid state, but it's so hot out here. It's like constantly evaporating, it's boiling. So that is all that condensation and that fog that you see. All right, pour just a little bit more.
It looks like soda, but very, very cold.
Yeah, very, 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 very cold. Oh yeah, that's good. All right, so we're gonna walk on over here.
Oh goodness.
And Anderson, when I say run, you run.
Okay.
Okay, so now what we're gonna do is we're gonna cap this bottle. All right, and then I'm just gonna throw it into that water. Liz is gonna put the trash can. Okay, over here.
Please.
All right, now you gotta keep an eye on the trash can because that pressure is building. Those bottles can withstand like 300 PSI, which is absolutely crazy. Because if you think about a car tire, it's like 30 to 40 PSI, but there's so much pressure building in that bottle and it is going to go boom. So just listen really. Yes! All right, that was so incredible. Wasn't that fun?
Yes, it was really fun.
So I love that experiment because sometimes when we're looking at physical changes and we're looking at just ice melting, it may not seem like it's really cool, but physical changes, just because something is explosive doesn't mean that it's not a physical change. That was a great example of a physical change and also an example of a change in state of matter, because liquid nitrogen, whenever it is really cold, it is in that liquid state. But as it heated up and as it was evaporating, it wanted to expand, which blew the bottle open and exploded the trash can and exploded all of those ping pong balls. That was so much fun. I had a lot of fun.
I had a lot of fun too, and it also taught me that ping pong balls aren't just for ping pong.
That's right, you can throw a ping pong party. But again, never ever try any of those experiments at home. We had safety professionals, I am a trained scientist, but they're fun to watch. And so now we are gonna turn it over to Keisha and Cruz, and they're gonna walk us through an example of a chemical change. And I want you to take a look at something. I want you to look at their starting materials and then what they end up with as their final product. And in a chemical change, those two things should be different. So, check it out.
I'm Cruz.
And I'm Keisha, and we're here at Southern Research in Birmingham, Alabama. So, what about that trip to the zoo the other day?
Yeah, that was really fun.
I know. What was your favorite part?
Probably the elephants when they were getting their teeth brushed.
Yes, that was my favorite part too. It was like, whoa, look at those elephants getting their teeth brushed. And remember what you asked me?
Oh yes, is it the same to elephant toothpaste?
Oh, well, we're gonna do an elephant toothpaste experiment today, but no, it's not the exact same type of toothpaste. But one reason we call it elephant toothpaste is because we're gonna see the size and different things. But we're gonna actually look at a decomposition reaction. Our decomposition reaction is going to include using hydrogen peroxide, also written down as H2O2 in the molecular formula. The decomposition reaction is going to break down into water, H2O, and oxygen gas.
Yes.
Now, one thing we do, we always see hydrogen peroxide in a dark color bottle because light will break it down. So that's why most time when you see it, 3% is what we buy at the store. It's very important that if you're doing this at home, you're using the 3% concentration. Higher concentrations are more dangerous, and so we always make sure that those are conducted in a science lab. But this experiment is safe to try at home, but we still want to practice safety. So we have our safety goggles that we're going to put on.
And our gloves.
And our gloves, yes. Make sure that you are conducting this with a supervised adult. And that way we know that you are being safe because you have the supervision of an adult or a science teacher if you're doing this one at school. So we'll start off with our active dry yeast, and we will use 1 tablespoon. So we'll put it into this beaker.
Okay.
Make sure it's leveled off, okay. Good. We have our 1 tablespoon, and I'll put the lid on that. And then we have 3 parts water, which means that we put 3 tablespoons of water in our graduated cylinder, and we'll pour that into our yeast. Now our yeast is going to serve as our catalyst to speed up our chemical reaction. And the type of enzyme we have here is catalase. And our enzymes, majority of them always end in ASE. So while I'm stirring this up, I'm gonna go ahead and let you measure out our hydrogen peroxide. And so you're going to do 1 cup of hydrogen peroxide. So you have a 1/2 cup here, measurement tool. So go ahead and measure, and you wanna use your funnel to pour that into there. And so you'll do.
I can move this over here.
Okay. And I'll just move this back out the way.
Yep.
All right, and so now let's do this. I can hold this for you if you need me to.
Thank you.
All right. All right, so we'll do a 1/2 cup, and then we'll do another 1/2 cup, and they'll give us 1 cup of hydrogen peroxide.
There we go.
All right, let's bring that a little closer, and I'll hold that funnel for you.
Thank you.
You're welcome. All right, let's go ahead and do another 1/2 cup to get our total of 1 cup. All right, and so that's why it's very important that we know what different chemicals we use in the lab, because even though this is hydrogen peroxide, it looks like water. That's why we never taste or we drink anything in the lab. We always practice lab safety. Okay, so now we'll put the lid back on there because we don't want to spill that.
Yes.
We'll put our funnel over here. And now I want you to go ahead and give you some dish detergent. You're gonna mix that in there along with your food color. You can pick which color you want. I'm just gonna keep stirring this yeast and make sure it's all active and ready to go.
Which one do you want me to do first?
Oh, go ahead and do your dish detergent. Okay. So pour you a good amount in there, about 1 tablespoon. Then you wanna lean it to the side, yes, and let it kind of run down the sides of the bottle as well. Good.
Yep.
Then we want to go ahead and put our food color in there, and then you want to swirl that mixture around. Okay, so you're going to choose green. So we're going to have green elephant toothpaste. Sounds good to me. Make sure you go ahead and drop that in there.
Okay.
That's why we wear gloves, because that food color can stain your hands. That's good.
We go.
All right, put our lid back on there. And you can go ahead and swirl that round and then get your funnel on top. And then we're gonna pour in our enzyme, which is catalase, which is gonna serve as a catalyst. Mm-hmm. Remember I said majority of the enzymes always end in ASE. And they're gonna help speed up different chemical reactions. We have enzymes in our body. And so we're gonna go ahead and get that mixed around good, so we see some bubbles in there.
And this is the part where it.
Yes, we're gonna see. Yeah, we're gonna see that foam. We'll let you pour it in there, and I'm gonna hold this.
Okay.
So here we go.
Let's go.
All right, go. Oh,
Can't
get it all in there. Oh yeah. Oh look. Oh, that is awesome. So we have liquid detergent that was placed in there because see what was happening. Remember, our hydrogen peroxide, which is H2O2, is breaking down to oxygen gas and to water. And so that oxygen wants to get out. And so that soap right there is going to act as surface tension and kind of hold and trap those bubbles in so that we can make foam.
So is that why the foam is raising up?
Yeah, we have our foam coming out because it didn't come out just like bubbles. And so it creates that elephant toothpaste. That's what we call it. Look how neat that is.
Yes.
See how it comes out, and we pick the colors like toothpaste. You know, toothpaste comes green, blue. I think that was awesome right there. You did a great job.
Thank you.
So now we know that we talked about a reaction that we call a decomposition reaction. So our decomposition reaction started with using, what was that?
This was hydrogen peroxide.
Hydrogen peroxide, also known as H2O2, 3%, which you can buy at home, and it breaks down into what two things we said? H2O, which is what? Water, and O2, oxygen, right? Yes. So yeah, and so that's what we did, and we had our enzymes that help to speed up our chemical reaction. Now we're gonna go ahead and we're gonna make some more elephant toothpaste, but in a much larger size. So this was our at-home version that's safe to try with your parents or another adult. But the one that we're gonna do over here, we always conduct those in a science lab. So let's get ready. Let's move on over to the other side of the lab bench. So now we're ready to do our science lab version of elephant toothpaste. As you see, we have much larger glassware. We have some really large Erlenmeyer flasks, 4,000 milliliters. This time, instead of using that 3% concentration of our hydrogen peroxide, we have a lab grade of it. And so it's at 30%, much stronger. That's why we're protecting ourselves. We also have covered up our electrical outlets just to make sure nothing gets into them when we make our elephant toothpaste. And the next thing that we have changed in this part of our experiment is that we now have a different catalyst. It's potassium iodide. And so that is the one that we are using instead of using our yeast. And so let's get started. Now, remember, this is a very strong concentration of hydrogen peroxide. So we want to be very careful as we pour. And so when you grab that, make sure you have a good grip on it, and you're gonna pour it into your large Erlenmeyer flask. And pour it slow, don't try to pour it too fast. Wanna make sure that all of this hydrogen peroxide gets into here. If it gets onto your skin, it can burn. That's why we want to make sure that we're practicing safety and we have on our lab gloves. Okay, so we can put our graduated cylinders to the side, because when this elephant toothpaste gets going, we want to make sure that we leave enough room. All right, the next thing we want to do, we have our detergent, and we're going to do like we did before. I'm going to let you start with the detergent first. So and while you're doing that, I'm going to go ahead and put in my food color, and then we can just switch and you can put your food coloring in.
How much should I put?
You want to put a good amount, because remember, this is a much larger container. And then you want to make sure it gets on the sides as well.
I can tilt it?
Yes, tilt it. Yes, make sure you squeeze it in there. Don't be afraid. Want to make sure. Yeah, I think that's good. That's a good amount. Okay, so now I'm going to put detergent into my Erlenmeyer flask while you put in your food coloring. So I chose green, you chose blue. And then don't forget, we want to swirl it around like we did before with the smaller container. So we want to get it mixed in well. So we'll just do a simple swirl. So swirl it around. See your little bubbles form?
Yep.
You want to swirl it the other way. Okay, don't be afraid to swirl it. And then we're going to put it back around about the center of our table. So now, all right, so we have it. We're now going to add in our catalyst. So this is where we're going to see that reaction occur.
Okay.
So we're ready to see that elephant toothpaste come on out. Okay, be very careful with that. We're going to pour at the same time. Wait till I open mine. Okay.
And we need to back up?
Yeah, once we pour, we're going to start to back up.
Okay.
So we're going to pour. Let's go 1, 2, 3. All right, now stand back. Woo! Look at there.
Whoa, that's
Wasn't
so
that
cool.
Awesome?
Look at all that steam.
Yes. Because remember, we are breaking down. We're doing a decomposition reaction. We got O2, and then we have another product that's part of this decomposition, which is H2O. And so here we are. It is coming out. We see our foam. Looks just like toothpaste.
Yeah, it looks like toothpaste, the stripes.
Yeah, the stripes coming through there and everything. Now, even though the elephants don't brush their teeth with this, this was pretty fun though, wasn't it? Elephant toothpaste, having fun with science.
Thanks for watching Alabama STEM Explorers. If you missed anything or you want to watch something again, you can check out our website at alabamastemexplorers.org. Maybe you have a question we could answer here on the show, and you might grab a cool t-shirt. Feel free to send us a video question or an email on our website, alabamastemexplorers.org. Thanks again for watching. We'll be back next week.
Alabama STEM Explorers is made possible by the generous support of the Hudson Alpha Institute for Biotechnology, translating the power of genomics into real-world results. Southern Research, solving the world's hardest problems. The Hawley Family Foundation, established to honor the legacy of Brigadier General Everett Hawley and his parents, Evelyn and Fred Hawley, champions of servant leadership. Alabama Works, a network of interconnected providers connecting business and industry needs to a highly skilled and trained workforce. Alabama STEM Council, dedicated to improving STEM education, career awareness, and workforce development across Alabama. Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, advocating for exceptional STEM education in Alabama. Alabama Math, Science, and Technology Initiative, the Alabama Department of Education's initiative to improve math and science teaching statewide.